Hello, everyone, and welcome to the sixth and the final video on the lesson on standard normal distribution, where we will make use of Microsoft Excel to help us compute for the area under the normal curve given certain situations and certain conditions. Now, in the previous videos that you probably watched leading to this video, we already made use of the Z table in order to determine certain areas under the normal curve or certain regions under the normal curve, and we also made use of an online application that we can um, work with in order to solve similar problems. Now, this time, we will use certain functions in Microsoft Excel to do the same process. So I will be presenting to you one data on the life expectancy and the percentage of the population per country that has access to basic water services. So the countries that we see over here in this list are countries in the Americas. So those that are found in either the North or the South America. And in this list, we have 34 countries. The life expectancies are also given in this column C, and the basic water services are given in column D. Now, I've already computed for the mean and the standard deviation for both of these two continuous random variables, life expectancy and access to basic water services. And these are the following. 72.92% of the population in the American region or in the Americas has or 72.92 years old is the average life expectancy of the countries in the Americas, with a standard deviation of 7.17 years. On the other hand, access to basic water services has a mean percentage of 93.14 or 15%. That means that around 93.15% of the population in the Americas have access to basic water services with a standard deviation of around 6.78%. Before we work with the problems that we see over here and answer these questions, we need to take note of one important assumption whenever we make use of the normal distribution, and that is the data that we are working with must be normally distributed. So let's take a look, and I will show you how you can determine whether or not a certain distribution is normal. Now, there are many tests that are available in different statistical packages that are out there. And we can also make use of the similar tests that we do on Excel. However, since we discussed the skewness and kurtosis in a previous video, we will make use of our understanding that a normal distribution must be symmetric and mesokurtic in order for it to be normally distributed. So that's the extent by which we're going to see whether or not the distribution is normal. Now, here's what we're going to do. I would like us to present the data on life expectancy, for example, by making use of a histogram. Let's start with that one. And I've already prepared a histogram here. And you can generate one for your own. And you would notice that the distribution is definitely not normal. In one of the laboratory activities that we did in the second quarter, we used the same data and we found out that there is one unusual value, and this is the value for Haiti, right? So this would automatically show us that visually the distribution is already not normal. But let's try to confirm that by making use of skewness and kurtosis. So let's compute for the skew and the value of the kurtosis of life expectancy first. All right, so let's use the skew function. Let us assume that not all countries in the Americas are included in this list. So just to be safe, we will make use of the function skew instead of the skew for population, and then select all of the values under life expectancy. The easiest way to do that is just select all the values under the C column by C colon C, and then just press enter. And you should be able to find that the value is negative 4.18. Now, you should remember in the previous lesson, we said that a negative skew, value for skew, would mean that the distribution is negatively skewed or skewed to the left, which is not what we want to see. So we need to find a way so that the skewness is equal or at least very close to zero for the distribution to be normal. Now, in terms of kurtosis, what we can do is compute for that value by using a similar um, function, which is kurt. All right. And then let's select the column containing the data set that we're interested in, which is column C. And then we press enter. And we find that it's equal to 21. So remember that our basis for kurtosis, as we previously presented, was based on the value 3. If it's less than the value 3, that means that the distribution is platykurtic. But if it's greater than 3, it's leptokurtic. And you would notice it's kind of obvious here, as we see that the histogram has a very defined sharp peak at 74.27736, right? Somewhere with that boundary. So there is going to be a problem. These values are going to be problematic. Now, what we can do is we can get rid of the unusual values or the outliers in this case, and let's try to see how that would affect the skew and the kurtosis. So let's find the value corresponding to 36, and let's delete 80 from this data set just to see that we would have a distribution that is closer to being a normal distribution. So let's delete that cell, and what we would see is a much better looking shape. Although it's not normally, it doesn't appear to be mimicking the normal curve. You would notice that the skew and the kurtosis are much more um, ideal for us. So it's still negatively skewed, but only by a very small margin from zero. And the kurtosis is also quite closer to 3. So if you want to continue ensuring that the scores or the data set becomes closer to a normal distribution, we can continue getting rid of some of the other outliers or extreme values here. But let's not do that. For the sake of this example, we will be working with this one, and we're going to assume that this distribution minus the data from Haiti is already normally distributed. Okay, so we're going to work with that assumption. But definitely when you go into higher statistics, these values are going to be more important, and it's necessary that you defend or you determine that a certain distribution you're working with is normal before you can make use of certain tests. And this is where the idea of parametric and non-parametric tests would come in, but something that would be reserved for more advanced statistics courses. All right. So again, we will answer the following questions with the assumption that the distribution is considered to be normal. Therefore, we can make use of the next functions that we will do. So let's start with the first question. What percentage of the countries in the Americas has a population with a life expectancy that is shorter than 75? So if you're going to imagine creating a sketch of the normal curve or the probability, the density curve, the normal density curve, and identifying 75 from a mean and standard deviation of 3.096 is somewhere very close to the mean, right? But just a little bit higher than the mean of 74.07. And since we are interested in the life expectancy that's shorter than 75, the region that we're interested in is to the left, of 75. Okay, so how do we compute for that value? We make use of the function normal distribution, which is norm.dist. Let's just type norm and activate the function that appears first in the list by double clicking on it. So what we're asked here is actually the value that we want to use as boundary, and that happens to be 75. But aside from that, we're asked for the mean, the standard deviation, and whether it's cumulative or not. Well, the mean and standard deviation values are already here. Another way that you can do that, well, you can just click on them. But another way that you can do that is you can also enter another formula right inside this formula. So that's what I'm going to do. For the mean, let's choose the average. And these are the values in column C. So C, colon C. And then for the standard deviation, let's press comma first. Let's enter stdef. And since we're working with the assumption that this is a sample, let's select C colon C again to tell Excel that we're working with the values under column C. And then finally, the question of whether it's cumulative or not, always answer in these cases. We always answer we always enter true because we're interested in the sum of the areas in the regions that are covered to the left. Therefore, we're interested in a cumulative distribution function. All right, so the answer is true. And then let's press enter. All right. Sometimes there would be some pop-up messages that Excel would prompt you to correct the formula, and you can just press OK. There probably may have been an extra parenthesis or an extra colon out there, so it corrects it for you. But you can double check the formula here above. And we're given the value 0.615961, which means that around 61.6% of the countries in America have a shorter life expectancy than 75. All right. So that answers the question posted here. Okay. So let's work with the second one. What proportion of the countries in the Americas have a population that live longer than 70 years old? So take note that the normal distribution function here works in the same manner as the Z table. It gives you the area to the left of the distribution. But in this case, we're interested in the population that is on the percentage of the population or the percentage of the countries in the list whose population have a life expectancy that's greater than 70. So that's the region to the right of 70. Therefore, we need to subtract whatever value we get from the normal distribution from 1. So we can directly find the answer by entering 1 first, minus, enter the function for norm dist, and then this time let's make use of these values that we already have over here. So the value of x is 70 because that bounds the region. The mean is this value. The standard deviation is this value. And whether we want it to be cumulative or not, the answer is true, right? So let's press enter. We have the same error message again. I guess I need to put the closing parenthesis at the end of the formula, but let's press enter or yes, and it should be able to give us the answer this time. So the correct answer or the proportion that we're actually interested in is in fact 0.905742 or 90.57%. So if you take a look at 70 years old, that's actually lower than 74%. So when you compare the region to the left of 70 and to the right of 70, the region to the right of 70 is definitely going to take a much greater space than the region to the left of it. That's why we have 0.9057 or 90.57%. So 90.57% of the countries in this list have populations that live longer than 70 years old. That seems to be nice na many people, at least in these countries, the population in these countries are able to enjoy a life as long as 70 years old, right? Okay, so let's continue with the last example. This time you're asked what is the probability that a randomly chosen country in this region has between 85 to 90% of its population having access to basic water services. So this time, we're going to work with the second continuous random variable, which is basic water services. So what I'm going to do is, well, we can directly enter the whole formula into one and get the final answer. But just so we get the hang of it, let's try to solve for each of these, using each of these values individually first, and let's try to analyze what exactly we're going to do with those two values. But if you're going to imagine a density curve, a normal density curve, identify 85 and 90. Take note that access to basic water services has a mean of 94. So both 85 and 90 are below or to the left of the mean, right? But we're interested in the region between 85 and 90. So let's work with 85 first. Let's identify how much of the countries in this list in terms of percentage, how much of them have less than 85% of its population having access to basic water services. So norm list of 85, that's the value, but the mean is given here. So let me just use that, and the standard deviation. And then if it's cumulative, we still enter true. This time, let me put on the close parenthesis and let's see if it works well. There you go. So this is for 85. Let me just move this value over here so we remember. This is the probability that, since we're using the actual values, we say x is less than 85, right? And then this is the probability that x is less than 90, because that's what the function would give us, the values that are less than, including the values that are also less than 85. And we'll talk more about that later, but I think you get the idea. So norm distribution of 0.0125, right? So wait, I got lost for a while there. So we're working with 90, and then the mean is 94, and then the standard deviation is this value here. And if it's cumulative, yes, it's true, and then we enter. All right. So these are the regions, the areas of the regions to the left of 85 and 90 respectively. But what we are interested in is actually the region between them. So um, since the 0.1558 also includes the region to the left of 85, which is 0.0125, we just need to subtract these two values so that we can find the probability that x is greater than 85 but less than 90. Of course, it doesn't matter if it's less than or equal to and greater than or equal to. We know for a fact that those values would still be equal. So subtracting these two values, we should be able to find that the final answer is 0.143324, and so on and so forth. Or simply 14.33% of the countries in this list have a population that has 85 to 90% of its population having access to basic water services. All right. You can also find that another function that we use in Excel, which is the norm inverse, can give you the value instead that corresponds to a certain probability. So, for example, how do we find 90 if we know that we're after the boundary that covers 15.58% of the individuals in our data set? So kung binigay, if what we're given is the percentage or the probability, how do we find the actual score? So just to double check, we need to find 90 here. And the probability is this value. So let me just click on it. Because if we're going to round it off, definitely we may not be able to, Excel may not give us the actual value that we're interested in. And then the mean is this value here, and then the standard deviation is this one. And then when we press enter, we should find that it's equal to 90. So this is this goes to show that we can make use of the norm inverse whenever we want, the norm inverse function whenever we're given the probability or the percentage, but we're after the raw score or the observed value in the data set. All right. So we will stop the lesson here, but I hope that you were able to learn a lot about the standard normal distribution and the different situations that we can apply it to. I hope that you're excited to look and you look forward to the next lesson on sampling distribution. Thank you, everyone.